Here we go. Section 1.2, graphs of equations. As you guys are writing, we're talking first of all about solution points, yeah? Solution. If it's a solution, that means it works. It's the answer, right?
Yeah.
However, have you ever seen in math a solution or an answer that ended up being wrong when you checked it? Okay, there are really like basically two different reasons that can happen. What's one reason? You found an answer, you checked it, it was wrong.
You did it wrong.
You did it wrong. Something went wrong in the process. However, in math, and especially this year, from time to time, there are going to be problems that you solve with totally legal math, but in the solving, you actually, by the math, by the algebra that you were doing, by the inverse operations that you were using, because of their nature, allowed incorrect answers in, which is weird. But by some of the math that you do, you kind of open the door for some incorrect answers to just kind of sneak in, which is a dilemma, because the math truly will say that an answer is, and it actually is not. So just kind of an introduction to that for the rest of the year. A point that you get, specifically when talking about solving an equation, is a true solution if, when you plug in, it results in what kind of statement? A true statement. And I know that seems so basic, right? You're like, that's dumb, it's math. You just solve for it, as long as you solve for it correctly, you have the right answer and you're done. But the problem is, some of you are going to do some great math. You're going to get some answers. One of them is going to be great, and the other one is going to be illegal, basically, without going in much more details. It's going to be what we call inconsistent. The math says that it's true, but when you go back to the very beginning and in the context of the problem, it doesn't make any sense, and it's actually going to be wrong. Just kind of a quick heads up for that. So then down below you see the example. How do you show whether 1/4 is truly a solution? Solve it. No, not good enough. Plug it in, plug it in. So when we plug it into our function, we have the 7, that's always true. We have the 3, that's always true. We're going to plug into two different spaces. The x, obviously, is the x-coordinate, 1, right? And the 4 is hence the y-coordinate. We have to make sure it works from the get-go without doing the extra math. Not to say that all algebra is illegal. It's definitely not, and it is very, very useful. But to check and make sure that an answer is truly a solution, you need to plug it in straight away without doing any transformations to the function. We end up with PEMDAS, right? Subtract or multiply? Which one first? Oh, yeah. So we have 4 is equal to 7 minus 3 times 1. And then we can go ahead and do the subtraction. Is 4 equal to 4? Yes, it's a solution. Good. Do you have to check every single problem that you do? No. However, I will give you warnings when some of the problems you're doing involves math that allows illegal answers in, and we have to get rid of them before we're done. Okay? If you want to think about it, squaring a square root is an example of math that can allow illegal points in, or illegal solutions. Next one. Point plotting. Oh, yeah. Makes it so I don't have to keep track. Sketching graphs. Now, come on, guys, think back. To the beginning of sketching graphs, probably you were sketching lines. Probably lines were the first graphs that you sketched. Followed not too long after, a chapter or two later, with parabolas. I remember because when I taught Algebra 1, that's how I did it. Some of your books are a little different, but not much. When you started sketching graphs, most of you were not taught y equals mx plus b and exactly what all those components were from the get-go. Instead, you discovered lines. You discovered them by making tables. And those tables can either be vertically oriented with like an x and a y coordinate, plug and chug. And probably back in Algebra 1 you had like this extra portion too where you had to actually plug it in and show your work. Maybe you were annoyed back then, but believe me, the more careful your middle school, maybe even ninth grade teachers were with Algebra 1, hopefully the better foundation you have. It's about that foundation. Oh, upper math is hard. But tables. sometimes in the very, very beginning, they probably gave you X values and told you to plug it in, right? However, as you got more capable with those tables, you were choosing your own X values. That's an O. You were choosing your own X values. And then you were plugging in to find Y. Because remember, Y's are dependent on, that's why they're called the dependent variables. You had to take those X values, plug into a particular function to find Y values. Something so basic, and yet in some problems can become, to be honest, like the most difficult step. At this point, you're kind of like, oh, we learned how to graph lines, we've learned how to graph parabolas. You would think you would never have to go back to a table, but look at those problems below. Look at the equations and ask yourselves, if you were given a quiz right now, no graphing calculator whatsoever, which of those equations would you probably, in order to get any work down, would need to resort to a table? Square root. Oh, yeah, right? You're like, I don't know what that looks like. That's fine. If I were to give you a quiz right now, the best thing you could do on that square root function is probably, whether literally writing down a table or thinking in your head, what if x is 1? What if x is 2? What if x is 3? Try to find some graph if you have to. And if you don't have your calculator, some of you are like, I can't do it, and you throw down the pencil and you walk out the room. Either literally or in your head. But you have a table that you can always go back to. Okay? That's not anything to be ashamed of. If you're stuck and you're trying to figure out a graph, sometimes we'll go back to a table. What other ones, some of you, to be honest, would be like, yeah, I wouldn't know how to do that one either. Which one? Yeah, probably the x squared one. Because some of you are like, I know it's a parabola, but where is it at? How do you find the vertex? Complete the square? Yeah. So to be honest, probably that one. Why am I not circling these ones? Hopefully they've become so second nature that you know, hey, they're both what, first of all? Lines. They're both in point, slope-intercept form, technically. And where would you start graphing lines? Yeah, you would start with the b, which on this one would be a -1. You can always put the point on this one you would start at, right? You can always get a point from the b, and then you would use your slope how? Right? Up 3 over 4-ish. This one you would have down 2 over 1-ish. Some of you might need to review that too, and that's okay. But these ones, we have a system hopefully mostly worked out. This one, you've worked on some, and this one you're like, anyway. There's no shame in sometimes going back to a table, just wanted to point it out. Okay? Now, clues. We basically have 2 clues, 1 equation, and we're done. First set of clues, intercepts. Nice thing is, last night's homework totally set us up for this one. You guys see that homework problem that had to do with intercepts? I even had you guys say the word intercepts when we went over it. 2 different clues. Intercepts first, we're going to cover it right now. Symmetry is going to come right after. And then we have 1 equation, a blast from the past, and then we're good to go. So intercepts. You guys are setting it up. This is just the foundation of graphing clues for any function, not just lines. Special points we can look for right off the bat are intercepts. X-intercepts are ones that have a particular x value, but no height, because it hasn't gotten off the x-axis, so the y is 0. Y-intercepts, points that have a y value or a height, that's not where the y goes. I'm saying, writing what I'm saying. Have a y value, we'll call it b just for sake of simplicity, but haven't gotten off the axis, so x is 0. So match it. X-intercept hits the x. Oh, we know that y is 0. Why am I writing this point again? To remind you that an x-intercept is an ordered pair. It's not just an x value. X equals is a line. We don't want that. We want a point, an ordered pair. Y-intercept, follow the pattern. Set x equal to 0 and solve for y. One more time, remember, it is an ordered pair, okay? So if in homework it says find the intercepts, find the intercepts, find the point, find the x and the y. But the nice thing is you already know half the point just based on what's there. I just want to raise your hands to vote. Think about it for a second. Which one do you think is harder to find? Pretty much all the time. Think, wait. How do you guys think the x-intercept is harder? How do you guys think the y-intercept is harder? How many guys are like, that was way too fast to vote? Then let's not vote. Let's try one and then answer the question. Now the crazy thing is, I'm going to zoom down here in a second. The answers are right there. You see the picture. So I want you to show the math that backs up the picture. What if you didn't have the graph? It's kind of a complicated one. If you can't read it, the function is y equals x cubed minus 4x. Y equals x cubed minus 4x. You can see the answers. Show me algebraically, mathematically, how to find answers. I can give you tons of them. Let me give you at least a head start. I know you can pull the answers from the graph. That's great. Show me the map that backs it up. Do what we put in our notes a second. Cheating. You guys agree? To start? Okay, which one's easier to solve? Oh, yeah, all day long, right? Y-intercepts, we love those. Those are awesome. Why? 0 cubed is? Minus 4 times 0 is? I'm doing exponents and multiplication first. So then y is equal to? Now, if y equals 0, what is my y-intercept? 0, 0. Thank you. Got one. Does that back up with our picture? The one place it crosses the y-axis? Yeah. Now to solve this, my question is, what would be your first step? And some of you would say, add the 4x. You're trying to use algebra, and it's really, really good, except it's really, really bad in this example. As soon as you do that, you're going to start losing, literally, answers. Because if you had added the 4x and divided both sides by x, you would have lost the 0, 0 answer. And if you had square rooted and only done a positive square root, not a plus minus square root, you would have lost another answer. What is the best, the only, from here on out, way of solving any function equal to 0? Factor. Anything in common? There's an x. I get x squared minus 4. Oh, I remember this. Whenever I have more than one factor, I set each one equal to 0. Right? So 0, add the 4, square root 2. There are 3 answers. Technically, you could add the 4 and plus or minus square root, or just say, you know what, there's a better way of factoring. What's that better way of factoring? Difference of squares. Right? X plus 2x minus 2. Set each one equal to 0, and what do you get? You get all 3. If you solve it any other way, it's not going to be so hot. Why, thank you so much. You would have only gotten part of the answers. I wrote them in a different order. Hopefully it doesn't annoy you too much. Intercepts. Intercepts. You guys remember yesterday how I talked about sometimes I might go faster than you? Is it better to listen and then catch up with the notes from online later, or frantically write down and listen to the whole video later? Which one's shorter? Listen, okay. If you can't write fast, listen. And write down this in your notes before starting homework tonight. Listen. There are 3 different types of symmetries. There's x-axis symmetry, which ends up looking like a function that can fold over the x and still be symmetric in the sense that they're the same on one side or the other. Y-axis symmetry, you can fold over the y, same on either side. And origin symmetry, where you actually have to fold over and down. A little weird, but the way it works. How can you actually see these symmetries? Let me give you, real quick, 3 different examples. Okay? The key is to plug in and see if it stays the same. For instance, if I was to plug in a negative y, question, what happens? Negative squared is a, anything change? No. It has x-axis symmetry. For the next one, if you plug in a negative x and it stays the same, let's check it. Negative x squared, y equals, a negative times a negative is a positive. Stays the same. The last one, if I plug in a negative x and a negative y, and it stays the same. What happens when I simplify? The y stays the same. What's a negative cubed? A negative. But it's different. No. It's really the same. The way we can see the symmetries is if when you plug in it stays the same. Now wait, what if we had tried this test, plugging in a negative y to this one? Could that have canceled out? Stays. Well, this one doesn't have x-axis symmetry. So when you plug in and it changes everything, it doesn't have a symmetry. When you plug in and it stays the same, it does. All right. I'm going to show you, there's 2 seconds. There is one formula, the last 2 problems of homework that we didn't write down. Shock and horror. However, you've seen it before and you can find it in the section. If you get to the end of homework, go find yourself a formula. It helps. We'll write it in our notes tomorrow. But I still want you to do section 1, 2. You're allowed to skip the last 2 or 3 that has to do with the circle. The rest, though, should be attempted. Bye, guys. I'll see you later. Any questions? I'll be here after school. Don't forget anything.
We should have more material that I can move.
I'm sorry.
Such as white out.